with that, and I'll cut that out of the video. With that, let's get started. Good afternoon, everybody. Welcome to another cloudy but exciting afternoon of Chem 170 Organic Chemist with your host, me, Dr. White. And we got a lot to do today, so I better get to it. All right, you should have seen over the weekend I sent out, and there's an announcement which I'll show you right now. This Wednesday I'll be giving test number two. And let's talk about the important information you should know about test number two. Thumbs up, people. Do you see? Someone said thank you. All right, I'll be giving it this Wednesday. It'll be online. On Tuesday afternoon, you'll be able to download from the D2L assignment area test number two PDF file, which will be password protected. On Wednesday, right after class, I will email you the password so you can get started on that. You have until, I got Thursday morning. Yep, that's right, Thursday morning, 10 a.m., give or take a half hour. I might even say 12, but try and get in by 10 to finish test number two and upload it as a single PDF file to the assignment area D2L. Should take you about 40 minutes, but if you need an hour or so, go right ahead. You know, let's face it, if you're not cheating, and you shouldn't, if either you know or you don't. Extra time usually doesn't help any students. So if you need a little extra time, that's okay. Now, test number 9 has 9 pages, 10 problems. Some of the problems are multiple part. In Chem 170, I have never, ever given a multiple choice question on a test or a final. All right, functional groups we'll cover: alcohols, thiols, ethers, reactions with ethylene oxide, epoxides, aldehydes, and ketones. The test point breakdown for test 2 is 11 points general knowledge and 34 points nomenclature. Nomenclature questions, as you've learned by now, are: here's the structure, give the IUPAC a name for that structure, or here's the common or IUPAC name for a molecule, draw the structure. And then reactions will be 60 points. And I think 3 or 4, I can't remember exactly, will be synthesis. The synthesis is give the starting materials for the following reaction, but the majority of the points will be, as we've done, give the organic product or products for the following reaction. If you notice, it adds up to 105, so there'll be 5 bonus points. Now, which are the bonus questions? I don't know. If this adds up to 105, you pick which you want to. Now, this test is, as with all of my tests, will not be open notes. And I put things in the test that I'll know if students are opening their notes, and that's called cheating. And other ways of cheating, please don't do, because I'll know, and I will do what's in my syllabus, which you won't want that to happen. Please don't. And today I'll be doing a review like I have here. And on Wednesday, we'll have our regular Zoom meeting with our lab and other materials. And that's it. Again, this Wednesday after class. Ooh, I forgot. Today's the Ides of March. So if you're Julius Caesar, watch your back. I don't know about you, but in high school, we had to read Julius Caesar to play. And I remember et tu, Brute, that's about all Latin I know, which, if you remember Julius Caesar play in history, on the Ides of March today, Julius Caesar was killed by being knifed by a bunch of senators, and the last one to thrust a knife into his back, so the story goes, I wasn't there, so I wouldn't know, but was Brutus. And when he did that, Caesar looked at Brutus and said, et tu, Brute? You too, Brutus? So much for English. And that's that. Any questions on test number 2? Looking at chat. Looking at everywhere else. All right, with that, today's game plan is, first of all, I've talked about test number 2 information that will be this Wednesday. I'll also, starting shortly, I'll do my world famous review for the next test, test number 2. I feel like Winston Churchill, V for victory. But anyways, test number 2, and then I'll go through the aldehydes and ketones problem set. And finally, we'll have some time. I'll start in the next chapter, carbohydrates, which will be on test 3, not test number 2, but I still have to get started on that. And with that, just one more thing I'd like to ask. Did any of you happen to think of organic chemistry when you went by a gas station and that the gasoline contains ethanol and alcohol? Did any of you happen to pick up a bottle of rubbing alcohol and see it contains isopropyl alcohol, which is an alcohol? Or did you happen to look at nail polish remover that you have in your house, or if you're in a supermarket or big box store, they let you pick up things and read the labels. I do it all the time. And think about nail polish remover contains acetone, which is a ketone. I hope you did, because it won't hurt to think about organic chemistry, because organic chemistry is all around us. I stole that from SpongeBob. And it won't hurt to think about it outside my classroom. All right, now that I did my, what would I be preaching from the pulpit, it's time to do the review. All right, one caveat. I should have mentioned for test 2, like test 1, every problem, every question on that test, I've covered the concept behind that question or problem at least twice, probably a lot more times in class. I never put something on a test other than your name I don't cover in class, which is a question, but not for points. And that'd be different. 2 points, what's your name? Boy, I hate to have someone get that wrong. Oh. But anyways, Dr. White just cracked up Dr. White, big time. But anyways, don't forget anything on the test. I've covered the concept at least twice, a lot more. Also in a review, I try and cover everything. If I cover it in a classroom, but not in a review, it's still fair game on a test. All right, we start out alcohols. What is an alcohol? Carbons with a hydroxyl group. How do you name them? The IUPAC name. Find the longest chain or ring that has the hydroxyl group on that carbon. Name it as an alkane or cycloalkane. Drop the E, add OL for acyclic, not in a ring. You need a number, and the carbon with the hydroxyl group has the lowest number, meaning highest priority. If it's in a ring and there are no other functional groups, which is what you see in my class this semester, you don't use a number because the carbon with the hydroxyl group in a ring will always be number 1. One name that's both the IUPAC and the common name is a benzene ring with a hydroxyl group, that's phenol, and you should know that. Now, we talked about common names. Common names, I'll never ask you, here's the structure, what's the common name? But I'll ask you, here's the common name, draw the structure. Why? Because you'll be seeing those on things you buy and ingredients labels, and you should know how to do that. All right, for alcohol, name the R group the same as the alkyl group it is, like methyl, ethyl, isopropyl, or T-butyl, then add the word alcohol at the end. And just to show you, rubbing alcohol, if you look at the label, they have different strengths now, but for many years, they only had 70% isopropyl alcohol and 30% water. Now, how do you make an alcohol? Well, this is the only reaction that's going to be in 2 different tests, and that is double bond acid and water. Remember, water is HOH, break the pi bond, one carbon gets H, the other gets OH, follows Markov-Nichols rule. Markov-Nichols rule is the carbon with the most hydrogens in the double bond gets this hydrogen, the other carbon gets the hydroxyl group. Now, the fun part, reactions of alcohol. Oops. If you have, move that down. If you have an alcohol carbon with a hydroxyl group, adjacent carbon has the hydrogen, you hit it with sulfuric acid, H2SO4. This little triangle means heat. Sometimes I do or don't put down to remind you that heat's pretty high, 180. And what happens is you lose water and you have a double bond formed, and it follows Zaseth's rule. The double bond you form has the most carbon atoms, important, most carbon atoms directly bonded to the carbon atoms of the double bond. And we went through this in the alcohol problem set. Now, fun reaction time, yay. All right, if you have an alcohol reacted with HX, where X is chlorine, bromine, or iodine, you replace the hydroxyl group with the halogen on the carbon in R that had the hydroxyl group. Now, if you had a double bond, this would be no good. So someone came up with, take an alcohol and react it with thionyl chloride, SOCl2. You replace the hydroxyl group on the carbon with the hydroxyl group with the chlorine. Now, I'll never ask on a test, but I talked about primary, secondary, and tertiary alcohols. Primary, 1R group on the carbon with the hydroxyl group. When you oxidize it, and I'm not asking you to learn the oxidizing agents specifically, we put a bracket, O closed bracket, meaning any oxidizing agent. You lose a hydrogen here, hydrogen there, form a carbon-oxygen double bond, and as you learned later on, this is an aldehyde. If you take an alcohol, secondary one, and react it with an oxidizing agent, you do the same thing, lose this hydrogen from the carbon with the hydroxyl group and the hydrogen on the hydroxyl group, and form a carbon-oxygen double bond, and you form a ketone. Now, tertiary alcohols never react, and since Dr. White teaches by his golden rule of teaching, which is never do unto my students what I didn't like done to me, therefore, I'll never, ever put on a test or a final where I ask you, what's the organic product or products? The words no reaction will never, ever be a correct answer. So that means I'll never put down tertiary alcohol plus oxidation. What's the product? Because the answer is no reaction, and I won't do that. Did it in the lab. Ooh, don't forget, the labs you did last Wednesday are due this Wednesday, or the lab you did. All right, next I talked about thiols, and thiols are where you replace the oxygen in alcohol with a sulfur. I didn't go any nomenclature, but important things you should know are, one, thiols stink. Just think of a skunk, because the skunk's weapon is spraying a thiol in water at, or thiols, there's a mixture, at whatever attacks it. I guess the skunks don't think their smell is skunky. Ooh, stinky. But thiols stink. Something you should know. Thiols are put into natural gas. And I'd like you to know about the fact that I talked about, and you should remember that back in about 1935 in Texas, there was that horrific explosion, an accident where a high school blew up because of a gas leak, and you couldn't smell it. Why? Methane is odorless, and you couldn't smell it. And because of that tragedy, the Texas state government had a commission. They said, we've got to have it so when there's a gas leak, you can smell it. And how do they solve that? They put in a thiol. And the thiol they use is T-butyl thiol. That's the common name. And so stinky, you only need 1 pound of that in a, or 1 to 4 pounds. I think it's 4 pounds in a billion pounds of methane, natural gas. And if you've ever smelled a gas leak, You know, you can smell it real quick. And that's because of the thiol, and you should know that. Next, I talked about ethers. Ethers is where you have an oxygen. Attached to that oxygen are two carbon chains, R and R prime. Now, I didn't go through expecting you to know the IUPAC name, but I did talk about the common name of ethers. How do you do that? Name each R group as the alkyl group it is, then add the word ether, like diethyl ether, which would be CH3, CH2O, CH2, CH3, two ethyl groups on an oxygen. Now, how do you make an ether? The only way I taught you, there's actually two, but this is the best way, and that's the Williamson ether synthesis. That's where you take an alkoxide, RO minus Na plus, plus an alkyl halide. I don't have here, but X should be chlorine, fluorine, or not fluorine, chlorine, bromine, or iodine. And the carbon with the halogen will be the carbon in R prime that the oxygen is bonded to in your ether. And you also make a salt. And if you remember, we went through some synthesis problems going backwards, figuring out what these are. And this is important to know what salt you make so you know what X is. Now, something at first glance that looks like an ether but isn't is an epoxide. And the only epoxide I talked about was ethylene oxide, even though there are a lot more, but we only have one semester, so I have to trim certain things. So we have time to talk about things that I think are more important to you, but this is important. And ethylene oxide is not an ether because it has different reactivity. Because it's in a what we call the strained three-membered ring, all the atoms are all strained together and they say, I want to be free. And you can break bonds real easily, unlike an ether, which you can't, because it's not constrained. This carbon-oxygen bond will break easily. And if we take an alcohol and react it with an epoxide, you will get this ether alcohol. The oxygen with the carbon with the hydroxyl group is the carbon with the oxygen in the ether alcohol product. Now, this is 1 molecule or mole of ethylene oxide. If you react N moles of ethylene oxide, you get the following: a poly, meaning many, ether alcohol. And we use brackets to have this repeating unit, and how many moles N of ethylene oxide you react with the alcohol determines what N here is the outside of the bracket. Now, common mistakes students make are they put the hydroxyl group inside. Wrong. Common mistakes students make, they put the hydroxyl group inside. Still wrong. Don't do that, please. And next, we start talking about one of my favorite groups in all, functional groups in all of organic chemistry, aldehydes and ketones. Aldehyde, carbon, double bond to oxygen with an R group and a hydrogen. Ketone, carbon, double bond to oxygen with 2 R groups on it. Aldehyde ketones. For aldehydes, find the longest chain with the carbon double bond to oxygen, which we call the carbonyl carbon. Excuse me. I'm going to scroll down, somewhere down here, I better have it. And the carbonyl group, and this is a carbonyl carbon, you should know, see, important, you should know how to describe it in a drawing it, carbon double bond to oxygen, how to describe it with words, carbon or carbon atom double bond to oxygen or oxygen atom. If we go back, aldehyde, you find a carbonyl carbon, how many carbons are in the longest chain that contain that carbon, name it as an alkane, drop the E and add Al. Since this is always going to be number 1, everybody knows that, you don't use a number. Now, word of caution, Alcohol, OLND. Aldehyde, ALND. Make sure on test number 2, you put OL or AL clearly. You don't want me guessing. So I have a 50-50 chance of guessing wrong. Is that an O or an A? I can't tell. And even though with your PDF file, I can enlarge it, sometimes it's hard to tell. So please be clear. Remember, aldehyde, find the longest chain, name it as an alkane, drop the E and add AL, no number. Can't have an aldehyde in a ring. A special aldehyde that is both the common and IUPAC name is benzaldehyde. If you remember the odor lab you did, benzaldehyde smells either like cherries, maraschino cherries, like Dr. Pepper too, or it smells like almonds, like marzipan. If you haven't had marzipan, you're missing a lot in life. You should. And that's how you do benzaldehyde. And that's a IUPAC name that was taken from the common name. All right, next, ketones, carbonyl, bond to oxygen with R and R prime. Find the longest chain that includes the carbonyl carbon, name it as an alkane, and it can also be a ring 2 cycloalkane. Drop the E, add ONE. For acyclic, not a ring, you need a number. And this carbon, carbonyl carbon, has priority, which means it gets the lowest number in the chain, starting from either end of the chain, never in the middle, or wherever that carbon is. For a ring, cyclic, no number, because the carbonyl carbon is always 1, it rocks. And IUPAC knew that, it rocks. And that's why it's always number 1. Now, there are 2 common names that I asked you to learn. The simplest aldehyde, let me move this up out of our way. The simplest aldehyde, R prime can be hydrogen, and this is called formaldehyde. Nobody ever calls it methanol, which would be 1 carbon methane, drop the E, add AL, but it's called formaldehyde. How it got that name, I don't know, but it's been that way for eons. Now, the simplest ketone is when R and R prime are both methyl, and that's called acetone. And if you remember, it's in nail polish remover 1 type. And that, nobody ever calls the IUPAC name 2-propanone. It's acetone. You should know these common names. Now, once again, you should know what is the carbonyl group, how to draw it, carbon, double bond to oxygen, how to describe it with words, carbon or carbon atom, double bond to oxygen. So I know of no more important functional, or not group, it's not a true functional group in all of organic chemistry to me personally than the carbonyl group. But again, I'm being biased because in my heart of hearts, Dr. White is a carbonyl synthetic organic chemist. Yay. Now, how do you make ketones and aldehydes? We've already covered this. If you take a primary alcohol, oxidize it, you get an aldehyde. If you take a secondary alcohol, oxidize it, you get a ketone. Now, a special reaction, which allows you to make a carbon-carbon single bond and special type of ketone, aromatic ketones, is Friedel-Crafts acylation. If you take a benzene ring and react, this is called an acid chloride, and you have aluminum chloride, trichloride catalyst, you'll form this aromatic ketone. The group without the chlorine is called the acyl group, which is why it's called Friedel-Crafts acylation. And as I talked about it in class, aromatic ketones, one of them are sunscreens, UV absorbers that help protect us from getting cancer, which I think is a good thing. And the other thing is for use as what's called an initiator, which I won't ask on a test, for photochemistry, which is used for high-speed printing, also for curing your nail polish. You have the type of nail polish that needs a light to cure, harden, or dry, you might call it. Now, let's look at reactions. The next four reactions, I will never, ever give a synthesis on, but you should know how to predict the product or products. And here, notice I have either a ketone if our prime is carbons, or an aldehyde, excuse me, if our, getting all choked up over this stuff, not really, but anyways, if our prime is hydrogen, it's an aldehyde reacted with an alcohol and acid catalyst. That's what H plus is. Keep your eye on the carbonyl carbon, what's attached to it. Our prime or hydrogen, our double prime is still there. You have a hydroxy group, oxygen, R from the alcohol. This is a hemiacetal or a hemiketal, which I won't ask you, but we'll learn later in the semester. If this doesn't form, no carbohydrates like starches. And the second reaction that Mother Nature also uses is to take a ketone or aldehyde now, react it with two molecules or moles of an alcohol, an acid catalyst was attached to the carbonyl carbon, carbon double bond to oxygen, R prime, there should be an R double prime that fell off. If you see it, let me know. Oh, that was an awful joke. Is still attached. And then from the two alcohols, that same carbon that was the carbonyl carbon, are two oxygens on each oxygen. There is our group. Now, I might have forgotten to talk about this in lecture, so I better do it now. If you have a ketone or aldehyde reacted with a special alcohol, ethylene glycol, acid catalyst, think of this as this right here, two alcohols, but they're in the same molecule. What's attached to carbonyl carbon is still there. And you have two oxygens like up here, then R is CH2, but they're connected together. For whatever reason, students tend to forget to put that bond there. Let's try one of these because I can't remember if I did one in class, so I think we should try one. And the question would be, give the organic products for the following. And I'll do this one, then I'll let you have some fun. What's different up here? Remember, when you're looking at an organic molecule, look for what's different. And I have a carbonyl with hydrogen and carbon. That's an aldehyde. Could have been a ketone. And what's different here? Ooh, carbon with a hydroxyl group. That's an alcohol, acid catalyst. But wait, not one, but two hydroxyl groups. So that's the same as two alcohols. And as you saw, keep your eye on the carbonyl carbon. R is CH2, but they're bonded together. Do you break carbon-carbon single bonds? No. And for some reason, students forget to put that bond in, which makes it wrong. And so here, what's our prime? This hydrogen. What's our double prime? That methyl. Then these two CH2 are R. And therefore, what's attached to the carbonyl carbon, R prime, our double prime are still there. I have two oxygens. What's my R group? CH2. But don't forget, you don't break carbon-carbon single bonds. And there you are. Now, this is called putting a protecting group on because you can take it off later on, just like if you were going from say your car to a building and it's raining outside and you don't want to get wet, use an umbrella or a raincoat. And once you get inside the building, you stop using it. And by the way, I should mention, I got my PhD from Michigan State. My research advisor, I was in his research group, was Dr. Roosh, who I'll forever be grateful for the strong foundation of organic chemistry he built inside of me or helped me learn how to do. And his advisor was the great organic chemist, Herbert Stewart. And that reaction I just showed you, putting on a protection group on a ketone or aldehyde, Dr. Herbert Stewart invented that. I guess you could say he's my grand research advisor, like grandfather research advisor. Yeah, why not? But anyways, true story. And we still hear a lot about Dr. Stewart from Dr. Roosh, because Dr. Roosh was a graduate student in his research group. If I haven't told you this, when you're a graduate student in chemistry, I don't know about the other disciplines, it's like being a plumber's apprentice. You learn about the basics, how to do things that a PhD chemist should do. And that's what you learn. That's how you get a PhD in chemistry, at least organic chemistry. Oh, guess what? I forgot to let you have some fun. Your turn. Have some fun. And for those of you can, if you can, turn on your webcam, because that helps me see what you're doing. If I were in a classroom, I'd be looking all around at all the smiling faces. For those who haven't checked, make sure you got enough gas for your snowblower tonight. Or you can get to your shovel. I'm tired of snow already. Enough. Oh, it warms my heart to see everybody working on organic chemistry. Thank you. Oh, it feels so good. And when you're done, give me a thumbs up. Hey, everybody's just about done. Everybody done? Going once? Going twice? Let's do it. All right. Question is, give the organic product or products for the following. Look at a molecule. Look for what's different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond. If we look here, carbon double bond to oxygen. With carbons here, I'll call it R prime. Carbons here, I'll call it R double prime. Now, R prime could have been hydrogen, but in this case, it's not. Again, this is R prime. R double prime, you can reverse it, doesn't matter what you call. And then, oh, look, hydroxy group on a carbon alcohol, two of them in the same molecule, but that's two alcohols, and acid catalyst, acid being H plus. Keep your eye on the carbonyl carbon, because what's attached to it? R prime, or if it was a hydrogen, which is not in this case, R double prime are still there. We'll have two oxygens, then R and R. Now, in this case, this is R, This is R. So what's attached to this carbon? R prime, R double prime. Then I'll have my two oxygens. What's R? CH2. But if you notice that these two carbons, I don't have four bonds to it. That's because this bond right here never gets broken. Students forget to put that in there, don't you? And there's your product. Speaking about which, before I forget, important thing for test number 2, 3, 4, and the final. I can't do enough easily. Never mind. But anyways, and the final. Do you break carbon-carbon single bonds? No. And you should also know how many bonds to carbon. 4. Uh-oh, it's broken again. 4. Let's see, it's broken on that side too. 4 bonds to carbon. I think I'm going to have my hands recalibrated. 4 bonds to carbon. Remember, 4. 1, 2, 3, 4. Check every one of your answers. If you got 5 bonds to carbon, 2 or 3, it's always going to be wrong. All right, let's move on. Now, once you have a hemiacetal, if you react it with acid and water, remember you can find acid and water. We'll find out later how this goes about with carbohydrates in your stomach. But for this reaction, what do you see that's different? This is one of only 2 cases I know where you have 2 single bonded oxygen to the same carbon, hydroxy group OR in this case. You have R prime or hydrogen, R double prime. And this is the reverse of making a hemiacetal. You get back the aldehyde plus the alcohol you would have used to make this compound. What's ever attached to this carbon with 2 oxygens still attached, and now you're double bond to oxygen, carbonyl. And here the R on the oxygen becomes this alcohol. The carbon with this oxygen is the carbon with this hydroxyl group. Next, ooh, look, again, this is the only other place I know in all of organic chemistry where you have 2 single bonded oxygens to the same carbon, and each carbon now has the R group on it. And this should also have an H, it fell off somewhere. And this should be R, well, I just kept the R double prime. And you get back the ketone or aldehyde you would have used to make the acetal or ketal, and you get the alcohol from here. If you want to put a 2 there, you can. I'm only asking, give the products. I never asked in this course, balance the equations on a test. All right, next. Oh, Dr. White's happy because I get to talk about my favorite hero in all of organic chemistry, the great French chemist, Victor Grignard. And Victor Grignard, right here, reaction of an alkyl halide, where X can be chlorine, bromine, or iodine, to magnesium, and you formed a Grignard reagent. And this is a very strong nucleophile. It attacks carbonyl carbons. And remember, don't switch if you put RXMG, I'll mark it wrong because that doesn't exist anywhere. Carbon is bonded to the magnesium, and the magnesium is then bonded to the halogen. Now, you take a Grignard, first step, second step acid, oh, the water, the O fell off here, and acid and water, just pretend there's no there. And then this attacks the carbonyl carbon, what's attached to it, R prime or H, R double prime is still there, and you open it up to an alcohol, and now you do something very special, very rare, very important. We've made a carbon-carbon single bond. The bond from this carbon that was the carbonyl carbon to R triple prime is on the carbon that has the MgX on it. The bond from this carbon to R triple prime is to the carbon that has the MgX on it. Now, the ketone or aldehyde, the carbonyl, is a double bond. Double bond, as you know, is pi bond, sigma bond. And pi bonds I can break with hydrogen and a catalyst. If I add hydrogen and catalyst, such as nickel, platinum, or palladium, what's attached to that carbonyl carbon is still attached, and you break the pi bond, each atom of the double bond, gets a hydrogen, you make an alcohol. And this is a good way you can get ketones or aldehydes from nature and make them into alcohols you need. Now, both of these would be synthesis problems, the previous four, and this reaction of the Grignard reagent with the ketone or aldehyde. Those 5 reactions I'll never put on test as synthesis, but I will put on, give the product or product. But this one and this one I can. Now, if you have a double bond, this will react with that. So Dr. H.C. Brown of Purdue came up with a new reagent he had discovered or created, invented, and he won the Nobel Prize for this and some other chemistry with these types of intermediates. If you take a ketone or aldehyde, react with lithium aluminum hydride, think of this as H minus, and this whole thing like MgX plus. It attacks the carbonyl carbon, second step acid and water, and you make an alcohol. Same as this, except this reagents will not attack carbon-carbon double bonds where this will. And finally, the aldol condensation. And this is an area, enolate anions, Dr. White did his PhD thesis on. Oh, good memories. Anyways, the alpha carbon of a carbonyl has acidic protons. That means you can remove those with a base. They'll form an enolate anion, which attacks the carbonyl carbon of another aldehyde or ketone. On my test, I won't put ketones. I'll just stick to aldehydes. That's my secret gift to you. And you open up this carbonyl, it's an alcohol, and you form something special, very rare, and that's let me move this out of the way, that's a carbon-carbon single bond. And this is called an aldol, OL, alcohol, aldehyde, aldol. And it's the aldol condensation. It's a way of making a much more complex molecule from simpler ones, which is always important. And that's the world famous review for test number 2. Speaking about review and stuff, don't forget, commercial from Dr. White. Tonight I'll have my office hour in 15 minutes from 6 to 7:15. Its Zoom link is in the syllabus and also on the introductory page at Chem 170. So if you have any questions, come on by. Also, as I mentioned last week, even though nobody took me up on it, but it's still available. If you'd like to meet with some of your classmates, come to my office hour and I'll set up a Zoom breakout room and you can meet privately with your classmates to practice anything you want. All right, let's do something fun before we take our break. And what could be fun on this soon-to-be snowy afternoon and evening? It's time to play that fun game, circle and name the functional group, 2 points each. If I can spell. And have fun. Circle and name the functional group, 2 points each. And remember, if you can turn on your webcam, that helps Dr. White do a better job. Makes me feel better, which is a good thing. And for those of you who have, thank you. For those of you who don't, well, if you could, turn it on if you can. I understand. Hope you're all having fun playing that fun game. Circle and name the functional group or groups, 2 points each. If you haven't noticed what Dr. White is wearing today, it's winter again. I'll try polling once more, and next time we'll do thumbs up. So I know some of you like thumbs up better. All right, I think everybody's done. Let's do this. All right, how do you play circle and name the functional group? You look for what's different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond. That's where the fun is. Oxygen. And here we have carbons here and here. That's an ether. Ooh, another oxygen with a hydrogen on carbon. And that's an alcohol. And here, ooh, and B, oxygen there, carbons here and here, and that's an ether. Ooh, oxygen here to carbon with carbons here and here, and that's a ketone. Remember, ketone is not spelled with a Y, but if you did, I wouldn't take off points. Ooh, hidden right here, hydroxyl group oxygen on a carbon. That's an alcohol. Oh, I think I threw everything in but the kitchen sink. Another oxygen, double bond to carbon with a hydrogen carbon. And this is an aldehyde. Aldehyde. And that's how you play that fun game. I'm going a couple minutes over. We'll still get our full break. That's how you play that fun game. Circle and name the functional group, 2 points each. Now, I make it into a nice, fun exercise, but remember, if you can't identify an aldehyde or ketone, alcohol, or ether, how are you going to name it? If you can't identify an alcohol, ether, aldehyde, or ketone, how are you going to show what it reacts? How do you know what it reacts? It's an important thing to know the functional groups and their names so you can do the nomenclature and reactions, which is the bulk of the points on test number 2. And more importantly, it's how to learn organic chemistry. All right, any questions on that so far? All right, when we come back from the break, we'll do the aldehydes and ketones problem set, and then we'll do a new chapter. And that will be on test number 3 material, not test number 2. And with that, all right, I'm gonna give you an extra longer break. Don't tell anybody, I'm being nice, okay? Shh. Come back at 2 o'clock. I'll see you then. I'm gonna go stretch. I'll see you at 2 o'clock. For those of you who are back, if you look at the screen, you can see the weather map for this area, radar that is, and you can see there's a huge amount of snow coming our way. And if I look out my window, which I did both front and back, I'd say we got anywhere from 3/4 inch of snow already on the ground. The wind is something fierce, and it's a snowstorm out there. It's a real blizzard. Well, and the good news is, hopefully you're all safe and sound inside your house. What's the, whoa, at least in my area in Schaumburg, so now the wind is 22 miles an hour and gusts up to 30. No wonder it looks like a blizzard out there. It is. Aren't you glad you're safe and sound? You didn't have to come to ECC? Because I wonder if they're going to close early. Probably, usually when a day like this, 5 o'clock, they'll close. So if this were a night class, you might not have it. Aren't there any with tears? It's sort of like, I'm happy, sad. Happy I'm inside, sad is outside. Look out, Dr. White's in a good humor mood, even though it's snowing out. I'm tired of the snow. Well, better that than ice. All right, let's get back to work. First of all, as always, let me remind you in my class, there's no such thing as a dumb question. Always feel comfortable asking questions. Next, don't forget, tonight I have my office hours. And if you have any questions about anything, I haven't figured out the meaning of life, but anything else, stop by and ask. All right, let's move on to the problem set for aldehydes and ketones. And just to be sure, thumbs up, people. Do you see aldehydes and ketones? Thank you. All right, let's take a look at it. First question, give the IUPAC name for the following. First of all, what functional group do we have here? Aldehyde. Find the longest chain, name it as an alkane, butane, drop the E, add Al, no number because the carbonyl carbon is always 1. Next one, ketone, 4 carbons, 2. Carbonyl, carbons here and here. Longest chain 4, butane. For a ketone, you drop the E and add ONE, butanone. But for an acyclic ketone, you need a number 2 because it's on carbon number 2. This is 1. Now, this is also a ketone. So I have a carbonyl, double bond to oxygen, carbons here and here. It's in a ring, and that's 6 carbons. Don't forget the cyclohexane. You drop the E, add ONE because it's a ketone, and then this carbonyl carbon is 1. You don't put a number there because everybody knows it's 1, but you number to give the other alkyl groups the lowest, and this would be 3-methyl-4-isopropyl. Now, since I'm not holding you to the IUPAC alphabet rule, don't tell anybody I'm being nice. Shh. But anyways, if you had put down 4-isopropyl 3-methyl-cyclohexanone, I would mark that correct. And here we have an aldehyde. Longest chain is 7, heptane, drop the E, add Al, heptanal. Oh, your favorite group, the methyl group. And we have not 1, but 2, so it's dimethyl. What carbons are they on? This is carbon 1, so that's on 3, that's on 5, 3,5-dimethyl heptanal. And if we look at F, also, if you want me to do 1, always feel free to ask. If we look at here, what's different? Carbon, double bond to oxygen, carbons here and here, ketone. Longest chain with the carbonyl carbon, 9 carbons. Nonane. Drop the E at ONE, ketone, known. What carbon is it on? Remember, common mistake on test number 2, other places is you always number acyclic chains, that means not in a ring, from the end. So either this is 1 or this is 1. And starting here, 1, 2, 3, that gives that the lowest number. And then on carbon 6, we have an isopropyl. So it'd be 6 isopropyl, 3 known. The other type of nomenclature question, draw the condensed structure for the following organic molecules. How do we do that? We start at the end and move right to left, right to left. At this right end, we see ALND, aldehyde. If that were an E, it would be hexane and 6 carbons, 3, 6, and the end carbon, either side, but Dr. White, as you know, likes to do it on the right side, but either one would be correct on the test. I have my aldehyde. Now, if we look right here, ONE, octane, 8 carbons, ONE tells me if this were an E octane, 8 carbons, ONE tells me I have a ketone. Where's the carbonyl carbon? Carbon 3. Common name acetone is this, which you can write different ways. Formaldehyde, I like writing this way because I think it's cooler. But if you write it this way, that's perfectly correct. And here we have ONE ending, ketone. If that were an E, cyclopentane, 5 carbons. I have my carbonyl carbon right here, ketone. And carbon number 2, which would be here, I have one of my favorite groups, the tert-butyl group. And I think the rest are self-explanatory. And let's move on to reactions. Ooh. What do we have here? Oxidation, O in a bracket, oxidation, primary alcohol. Oxidize a primary alcohol, lose hydrogen here and here, you get an aldehyde. What's our methyl? And this is the aldehyde you get. If I have a secondary alcohol, carbon with the hydrox group, carbons here and here, this so happens in this ring, no, it's not a square, this organic chemistry, that's a ring. These are connected together. I lose the hydrogen there, which you don't put on a ring, and this hydrogen, I form a carbonyl, and I form, Dr. White's happy, I love cyclic ketones, which this is. So is Mother Nature. And here, same thing, secondary alcohol, lose this hydrogen, you form a carbonyl. What's attached to that is still attached, because do you break carbon-carbon single bonds? No, you don't. I have another one. I got enough oxidation. All right, new reaction. What do we have that's different? Benzene ring. By the way, my software sometimes likes to do left justified. This is the same as CH3. You can put on the end here, the H3 on the outside, right or left. I missed that, usually I correct it. But carbon, carbonyl, chlorine to the same carbonyl. This is an acid chloride, an aluminum trichloride catalyst. This is Friedel-Crafts acylation. And you put the acyl group on the benzene. Don't forget the double bonds or circle in the benzene ring. What's our methyl? And here's the aromatic ketone you make. And here we change the R group, same reaction. We form this aromatic ketone. Here I put an even more interesting one, where R's benzene ring, still benzene plus an acid chloride, aluminum trichloride, and you form this aromatic ketone, which is called benzophenone, which I won't ask on a test, but for many years that was the active ingredient in sunscreens and suntan lotion to protect you from the harmful UV light of the sun. And someone in Europe found that there was this tiny, tiny, tiny possibility it might give you skin cancer. And I debate, rightly or not so, they said, oh, we got to take this out of all our products. And that came to the United States. So the manufacturers of those compounds said, all right, we'll pop a methyl group on one of the benzenes. It's different. And I don't know if it had that much of a difference in skin cancer formation. I think it had was a little safer, but I don't know how bad it was. I guess if you're in a family, I haven't, but my brother-in-law and my nephew are, which are susceptible to skin cancer, especially from this being out in the sun and those types of molecules, that is important. All right, let's do this one. What do we have? Aldehyde, alcohol, acid catalyst, aldehyde or ketone plus alcohol, acid catalyst. Keep your eye on the carbonyl carbon because that's where the fun is. And what's attached to it, R prime or H, R double prime is still there. This reaction opens up the hydrox group in OR, and the R comes from the alcohol. Carbonyl carbon, R is H, R prime methyl, still there. OH, let me move Dr. White. And R is O, CH2, CH2. And if you do it with a ketone, same thing. This is R, this is R prime, carbonyl. My R group, acid catalyst, what's attached to the carbonyl carbon, which is now this carbon with two oxygens, is still there. You have OH and OR prime. Now, if you have two molecules of a alcohol with, this is a ketone, carbonyl carbons here and here, and it could have been an aldehyde, two molecules of an alcohol plus acid catalyst, the carbonyl carbon becomes this carbon with two oxygens. On the oxygens are from the alcohol. On this carbon are R prime or H and R double prime. Well, in the ring, that's this R prime and R double prime. Here's my carbonyl carbon, which becomes this carbon right here. And I have two oxygens, and what's the R group? Isopropyl. This thing. 6 months ago, if I said isopropyl methyl or alcohol, would you even know what I'm talking about? Think about how much you've learned in the short time we've been together. And it's organic chemistry, and hopefully it hasn't been that painful. Hopefully it might have been even a little fun. And you should be proud of your accomplishments. I am. Make sure you do the practice problems so I keep on being proud of you on Wednesday. And the same thing here, two molecules. Ooh, let's do one for you to try. This might be a little challenging, but let's see if you're up to the challenge. In case you forgot, for today only, I'll help you out. And it's your turn to have some fun. So on this awful snowy Monday afternoon, we're all having fun doing organic chemistry. If I say fun enough times, you'll think it is, and it is. And for those who finish early, please be patient. I try and give everybody time to do it. And since some of you like the thumbs up as opposed to the Zoom poll, this one, when you're done, I know one person already is, give me a thumbs up. All right, looks like everybody's done. Let me give you another 8.7 seconds. 0.6, 0.65, time's up. Let's do it. All right, if we look at this compound right here, what's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? Oxygen to a carbon, carbonyl. I have carbons here and here, they're connected together, but this is a ketone. It could have been an aldehyde. Plus, what's here? Ooh, hydroxy group on a carbon. Not one, but two. That's two alcohols. And what do we get? Keep your eye on the carbonyl carbon. What's that? And sometimes on a whiteboard, the same thing will happen. What's attached to it? R prime and R double prime are still there. You'll get two oxygens, and the R group on the oxygen comes from the alcohol. Well, here's my carbonyl carbon, what's attached to it. The ring will still be attached to it. Same thing with this methyl. This carbon is this carbon right there. Then you have two oxygens. What's R? CH2. CH2. Now, if I stopped here, you'd notice something. There's only 3 bonds to carbon. And no, you can't do that. So why not? What happened? You don't break this bond right here. And students forget to put that in there. I'm reminded you don't. And that's how you have some fun with organic chemistry. Now, if you take a molecule, react it with acid and water, what's different? This molecule in D has 2 oxygens bonded to the same carbon. That's rare. There's only 2 cases. This is one of them. This would be a hemiacetal or acetal or ketal. Carbon with 2 oxygens has R prime or H, in this case H, and R double prime, which is CH2, CH3. Oxygens, what's R? Methyl. What do you get back? The carbon with 2 oxygens, double bond to carbon. What's attached to it, R prime or H and R double prime are still there. And the R group from the oxygen becomes this alcohol. If you want to put 2 there, you can. If not, you don't have to. Over the years, I've seen students put down, think they have to put the quotes there. No, this is my way of showing you don't have to do it. And you get back this aldehyde plus this alcohol. Ooh, let's look at F. Dr. White.
Question?
I do questions, Tom.
Okay, for D, you said that that's a hemiacetal or acetal?
It's an acetal.
Acetal?
I will
Okay.
never ask that on a test, but other courses may use it, so I'd like you to be familiar with the name. And you can always go back and look at my videotape or your notes. How do you tell the difference? Acetal or ketal, both oxygens have carbons on it.
Okay, so then also for C.
Have you ever heard of a hemi engine?
Yeah.
Half. Well, hemiacetal or ketal, one of the oxygens has a hydrogen. But I'll never ask that on a test, but It's a good question because all questions are good questions.
Okay, so then for number C, or letter C, the product of that equation is also a
Nope.
hemiacetal.
Look at C, the oxygen. Do you have one with a hydrogen or not? And the answer is no. So
Okay.
that makes it an acetal or ketal.
Okay. Thank you.
You're welcome. And now you knew everything you want to know about acetal, hemiacetal, ketal, and hemiketals. And for other classes, that may be an important concept to remember. All right, let's look at F. And here I did the chemistry instructor's favorite trick on a test. I put a big, scary molecule. No, you look for what's different. Carbon with two oxygens. This carbon has carbons here and carbons here. The oxygens have carbons. And what it is, oh, where is it? Right here, I pissed. Acetal or ketal, acid and water, you got back the aldehyde or ketone you would have used to make that compound, plus the alcohol. 2 is optional. And here, if we look at F, what's R and propyl? This whole ring are the 2 R prime and R double prime. The carbon with 2 oxygens becomes a carbonyl carbon. Then my R group, the carbon with the oxygen, is a carbon with the hydroxyl group. Now, moving on. Ooh, hydrogen, a catalyst. Remember, carbonyl, pi bond, add a catalyst, and catalyst can be nickel, platinum, or palladium to break the pi bond, and each atom of the carbon oxygen double bond gets a hydrogen. So here, each atom gets a hydrogen. What's attached to it, methyl and ethyl, is still there. You can write it this way or you can write it that way. I have a piece of paper signed by the Board of Regents of Michigan State University saying, I understand that. And here I gave another example, hydrogen catalyst, ketone. Break the pi bond, each atom, carbon and hydrogen of the carbon oxygen double bond, get a hydrogen, you don't show it on the ring, you get this alcohol. Now, when you use lithium aluminum hydride, LiAlH4, water break, and second step acid and water, same thing happens, but this will only react with carbonyl compounds like ketones or aldehydes, not double bonds, which this would. Even though in this class, I'll never put on a test at this point where you have more than one functional group. We get into real life things like sugars, then Mother Nature has done that. And let's look, we have a ketone, break the pi bond, and each atom of double bond gets a hydrogen. Same thing here. And it's key to always remember, do you break carbon-carbon single bonds? Now here I forgot to put something in, so I better do this real quick. I don't want you to feel cheated. And why don't you try this one for your fun enjoyment on the snowy afternoon in Chicagoland? What would be the organic product or products for the following? 3 points each. And for those of you with your web camera on, thank you. And real people out there. I did thumbs up last time, so let's do a poll time. Aren't you glad I'm not taking a poll tax? Oh, that was bad even for me. Well, I think everybody's done, so let's do this. All right, how do we do this? We look at what's different. What's not a carbon-carbon single bond or carbon or hydrogen atom? Ooh, halogen on a carbon, Rx. And magnesium, I made the Grignard. This is my R group, so I'm going to redraw it. And which carbon has the halogen? This one. We bond to magnesium, and the magnesium will be the iodine. And that's how you make a Grignard reagent. Now let's react it. And if we look at, say, B, if I have, what is this, an aldehyde, carbonyl with hydrogen and carbons, and it could have been a ketone. First step, I reacted carbon-carbon magnesium chloride, a Grignard. Remember, X here can be chlorine, bromine, or iodine. Second step, acid and water. What's attached to the carbonyl carbon, our prime or hydrogen, our double prime is still there. The carbonyl opens up to an alcohol. Then you do that special thing. You make a carbon-carbon single bond. And here for B, we have the carbonyl. And what's attached to that, this carbon now, hydrogen methyl, comes an alcohol. And notice here, my R triple prime is 2 carbons. The carbon with the magnesium halide, in this case magnesium chloride, is the carbon carbon bonded to the carbon with the hydroxy group. And notice in one simple step, simple molecule here, simple here, we've made a pretty complex alcohol. And that's the beauty and the strength of the Grignard reaction. Oh, Dr. White's going to have a lot of big smile on his face. What do we have here? Ketone, Grignard. Second step, acid and water. Here's my carbonyl carbon. What's attached to it is still attached to it. Opens up to an alcohol. My R triple prime is bonded to that carbon. What carbon has the Grignard? The center of 3 carbons. And this is how you make that alcohol. Next, ooh, 2 of the same aldehyde, sodium hydroxide. I apologize in the problem set, forgot to put water there. I've got it here now in the answer. And if you have an aldehyde, react it with base and water. The alpha hydrogens, the hydrogens on the carbon bonded to the carbonyl, are acidic. You form the enolate anion that attacks the other carbonyl, opens it up to an alcohol. And you do that special thing, you get a carbon-carbon single bond. And here, ethyl is R, so this attacks this carbonyl. Remember, you lose 1 hydrogen, always check there's only 4 bonds to carbon, and I form a carbon-carbon single bond, open this up. What was attached to this, CH2R, in this case ethyl, is still CH2 ethyl, or 3 carbons. And that's how you do it. Now here, does benzene react with sodium hydroxide and water? And the answer is no. But I have 2 aldehydes, and I formed the enolate anion and attacks that because the ring was in the way. Oh, look, the world's longest carbon-carbon single bond. But notice how I start with a simple molecule. I make this very complex molecule. And that, oops, and that's it for the aldehyde and ketone problem set. Anybody have any questions, observations, thoughts? Other than, oh, it's snowing out. All right. I have covered everything for test number 2. Obviously, I finished last week. We did the problem set and a review. So don't forget, Wednesday will be test number 2 after class. I'll send out the password. You have until next morning to finish. So you know what time it is? It's new chapter, new functional group time. And we're going to get into some stuff you'll love to get into. Now, this coming new chapter, we're going to talk something that's pretty sour. You don't want to do shots of it. It's sour. But we're going to get into stuff that smells so nice. Oh, is that nice? So we got a lot of good stuff to get into. And I'm going to get into some topics you'd never believe Dr. White could talk about. Plus, I'll even get into stuff that's in your refrigerator, maybe. Really? Yep. So, what's this new chapter? First of all, I got to open it. That would help. Give me a second while I close some stuff down. There we go. All right. Thumbs up, people. Everybody see chapter 10 on their screen? Thank you. All right. This new chapter is carboxylic acids and their derivatives. Derivatives is a fancy word meaning things that are derived or made from something else, in this case, carboxylic acids. And a carboxylic acid, new functional group time, yay! And it contains a carbonyl, carbon double bond oxygen, and a hydroxy group on that same carbon, and it's called a carboxylic acid. So let's look at the general formula for carboxylic acid. Now I have it here. My software likes to forget there could be a carbon here. Every bending line is carbon. And one easy way to draw it is this way. Or if you want to show pure bond angles, you can draw it this way. This is an oxygen. And this is, guess what? It's a carboxylic acid. And sometimes you'll see it written like this or like this. Later in the semester, I may write it a little like that, but for the most part, I'm going to write a carboxylic acid, carbonyl, hydroxyl group, R group. And this is a carboxylic acid. And I worked for a company that made carboxylic acids and also other things like that. I worked for a number of companies that made a lot of different chemicals. Now, how do you name a carboxylic acid? Well, you find the longest chain, which includes the carbonyl carbon of the carboxylic acid. You name that as an alkane per IUPAC rules you learn, and then you drop the E at the end of the NANE for the alkane and replace it with the letters OIC and the word acid. Now, the carbonyl carbon, because it rocks, and just like an aldehyde and a carboxylic acid is always carbon 1, therefore we won't put that number there. You number all and name the other substituents as we've already done. And this one I've never really encountered, so you don't either. When a carboxylic acid is attached to a ring, it's called carboxylic acid, ending like cyclohexane carboxylic acid. And I've never used that. I'll show you what we do use that's more likely. So let's have some fun with carboxylic acids. So let's put a carboxylic acid up on the screen or the whiteboard. Bet you didn't know I was so famous they named the whiteboard after me. If you believe that, I got a bridge in downtown Chicago. I'll sell you cheap too. Not. All right. Everybody see it on your screen, the whiteboard with thank you. Now, look for what's different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond. Ooh, carbonyl with a hydroxyl group on the same carbon, carbon's here. This is a carboxylic acid. How do you name it? Find the longest chain with the carbonyl carbon. 1, 2, 3. That's propane. Drop the E, add OIC, the letters OIC, and the word acid. And this is always number 1. And because of that, we don't put a number there. So I'm done. Propanoic acid. And that's the name of this compound, the IUPAC name. And Dr. White's going to share what would be the name of that compound. Remember, drop the E, add OIC, and the word acid at the end. Find the longest chain with the carbonyl carbon, this carbon right here. Now, how you have bad hair day? Dr. White's having a bad arrow drawing day. That's better. I think, is everybody done? Going once, twice, everybody's done. All right, what do we have that's different? Ooh, carbon, double bond to oxygen, that same carbon has a hydroxyl group. I've got carbons here. I have a carboxylic acid. Remember, count the carbons in a chain, including the carbonyl carbon, carbon double bond to oxygen. 1, 2, 3, 4, 5. 5 carbons, as you know, is pentane. Since we have a carboxylic acid, drop the E at the end, add OIC and the word acid. Since this is always carbon number 1, everybody knows that, no number, I'm done, pentanoic acid. Ooh, let's try another one. And here's one for you to have fun with. what would be the IUPAC name of the following molecule? Oops, let me get out of the way there. And now you can write it down. I think everybody's done. Let's do this. And the question is, what's the IUPAC name for this compound? Right here. And what do we have that's different? Ooh, right here. Carbonyl, double bond to oxygen with a hydroxyl group, OH, on the same carbon, the carbon's here. And we have a carboxylic acid. And now, how many carbons in the longest chain with the carbonyl carbon? 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, 6, 7, 8. And I hope you all agree 8 is larger than 5. So we have octane. And since it's a carboxylic acid, we use the endings OIC in the word acid. So it's octanoic acid. Everybody knows that this is carbon number 1. This is 2, 3. You never put 1 there because everybody knows that. And on carbon 3, I have an isopropyl group, 3 carbons, center carbon. So this would be 3-isopropyl octanoic acid. Now, there are 2 types of nomenclature. One is, here's the structure, give the name. The other is, here's the name, draw the structure. And how would I know what to draw with this name? I'm going to start from the right and move left. Word acid and the ending OIC, that immediately tells me I have a carboxylic acid. And if this were replaced with the letter E, I'd have heptane, 7 carbons. And the N carbon, I always draw it on the right. You could do it on the left, has a carboxylic acid. And I know, and I haven't done this in a while, so I better do it. There are 4 bonds, yes, 4 bonds to carbon. So I can now put in the rest of the hydrogens. And this is heptanoic acid, 1, 2, 3, 4, 5, 6, 7 carbons, including the carbonyl carbon. And that's a carboxylic acid. Now, if I look at the clock, it's about time to take a break. So instead of rushing through one real quick, which isn't polite to do to you people, let's take a 5-minute and 30-second break. Don't tell anybody, give me an extra 30 seconds. And I'll see you back at Oh, actually, it's no bigger break. I'll see you back at 2:50. I'm gonna go look out my weather window and be disappointed in the weather. I'll see you in 5. Time to start again. Dr. White has a nice whistle collection. The only thing I couldn't find is the old style. I had one, old, not when I was a kid, but now it is a policeman's whistle from Chicago. I'm going to have to track one down. I had one and it got lost years ago somewhere. But anyways, good news. I looked out the window. It's windy as all heck, but it's slowing down a little. And as I looked out my front window, I could see the street in front of my house has been plowed already. Now it's time for a quick history and political science lesson from Dr. White. Back in the winter of 79, I think it was late January, early February, we had one of the worst snowstorms in Chicago history. And I lived in Chicago at that time to get to meet people better, more in Chicago, because I wasn't really from Chicago, I was from the suburbs. I'd moved back from grad school in Michigan State. I joined the Democratic Party, then known as the Machine. And I got to know people, and I worked a precinct for the party. And we had a mayor then, Mayor Blandick, who was, put it politely, an idiot. We had this monster snowstorm. You could barely walk out of your house on the street. Snow drifts were up beyond your waist. I'm talking about for 10, 15 feet down the center of like Sheridan Avenue, which is a major street. Next morning, Sunday morning, I was able to make it out to Sheridan, about a half a block from my apartment building. I walked down the middle of it. There are no cars on it. It was packed with snow. Well, Monday, Blanda gets on TV and says, there's nothing wrong in Chicago. We're doing okay. No, there was a lot wrong. And finally, we got dug out. Took us about 3-4 days for things to get back to somewhat sense of normal. It was that bad. And there was a very, how should I say this, very sharp politician. There were rumors of what else she was, but I'm not going to go into rumors. And that was Mayor Byrne, who wasn't the mayor then. And that April, end of March, April, there was a primary for the Democratic mayor. Long ago, someone got smart and decided we're not going to have the mayoral election when there's a November election. In case things go south, we don't want to lose the mayorship of Chicago. So it's always a couple months after the actual election in November of 78. And Blandick should have won in a landslide. But because he was an idiot and got on TV and said, everything's okay when it wasn't, Mayor Byrne had a very simple commercial. I can still picture it. This is decades later. On an L stop, elevated train stop, she's standing there and it's slightly snowing. And she says, when I'm mayor of Chicago, I'll make sure the streets stay open. And she won the landslide and she couldn't. And because of that, and here's the political science lesson, every politician in Northern Illinois learned, if you don't keep the streets open in a snowstorm or afterward quickly, you're going to be out of a job. So wherever you live, by tomorrow, the streets are going to be pretty clean. Why? Because those politicians still remembered that lesson. All right, let's get back to carboxylic acids. And I'm not going to even charge you extra for that political science lesson or history. All right. Question is, how do you draw the structure from the name of a molecule? And in this case, carboxylic acids. You always go from the right, move left. OIC acid, carboxylic acid. The carbonyl carbon is always carbon number 1. And here's 3 points. Draw the structure for the following. Butanoic acid. Your turn. And I hope you all enjoy having fun with organic chemistry in the comfort of your home so you didn't have to go out in this awful driving weather. Even though I have a four-wheel SUV, which still doesn't matter because if the other people are not driving safely, I can get hit. It almost happened once years ago on 355. Guy zoomed past me in a snowstorm, started doing 360s. I was about to slam into my car, and I said I had two things I could do. I could stay there and get hit or slam on the gas. And luckily with four-wheel drive, he missed me by about 3 inches. All right, let's do this. Question is, how do you draw the following molecule? Start from the right, move left. OIC and the word acid, carboxylic acid. And therefore, if this were an E instead of OIC and drop the word acid, nonane, 9 carbons. And the N carbon, I like to do the right, you could do the left, would be a carboxylic acid, carbonyl with the hydroxyl group. And then I know there are 4 bonds to carbon, so I can put in my hydrogens. And that would be no acid. Oh, let's do another one. And remember, the carbonyl carbon is carbon number 1. And why don't you try this molecule? Draw the structure for 2-ethyl hexanoic acid. 3 points each. While you're doing that, I'm going to get a refill because I'm out of water. Oh no, I'm going to dry up. No, I won't. Dr. White will be right back. All right, everybody done? Thumbs up, people. If you're done, give me a thumbs up. I think everybody's done. And let's do it. How do you know what to draw? You start from the right, move left. OIC and the word acid, and that's a carboxylic acid. Carbonyl, carbon double bond oxygen with a hydrox group and R group. If this were an E, no OIC or the word acid, that'd be hexane, 6 carbons. And the N carbon is a carboxylic acid. Remember, this carbon is 1. As I move this way, ooh, ethyl group on carbon 2. And sorry, I didn't turn my picture on. I'm here. And now I'll put in my hydrogens. And you know there are 4 bonds to carbon. And this is 2-ethyl group on carbon 2, hexanoic acid. by the way, I do have to tell you something about this molecule. This is a really evil, nasty molecule. Why? Because it gave me about 6 months, not 6 months, 6 weeks of hell. I had done a reaction that made a new product using a certain aldehyde, and I'll show you the chemistry later on, but I'll tell you the story now. And I was about to take it, this new product, new reaction from the plant, from the research lab and the pilot plant to the plant. For those who aren't familiar with, in a chemical industry, when you discover something new, you do it in small scale in the lab up to about 1 pound, and then you scale it up. Think about if you were making breakfast for yourself and you made 2 scrambled eggs. Well, you know how to make 2, no big thing. What if you had 10 people over and you had to do a lot more at the same time? Well, you need maybe to think about, how do I do that? Do I get a bigger frying pan, or do I do it 2 batches? And that's called scale up. And in the chemical industry, we have what's called a pilot plant. And pilot plant, or in a lab, you usually go up to 1 pound or so, maybe rare couple of pounds. In the pilot plant, you usually do about 500 pounds, which is about 55 gallons. And you learn about what problems you have, but you're not wasting a lot of chemicals if you have money, if you have problems. And then you take it to the plant. And the plant is big time scale up. Think about making scrambled eggs for 10,000 people at the same time. And the plant I've worked at usually go from 40,000 per batch or reaction when you do it once, up to, I've been in plants where we've used 160,000. To give you an understanding, how many of you are familiar with a tank wagon, the vehicle that delivers gasoline to a gas station? Those are standardized, 40,000 pounds, 5,000 gallons. So when I would do a reaction of plant, we're doing anywhere from 1 to 4 of those. That's a lot of money. Well, anyways, right before we took it to the plant, it's standard to have a meeting with the plant manager and the vice president of production, myself, and maybe my boss and a few other people, engineers from the plant. And I was at a meeting for this new reaction of mine. And the production manager at the plant manager said, can you go back and do a couple experiments in the lab? I'm concerned about this. I said, no problem. He had valid concerns. Well, what should have given me a product that was a liquid, all of a sudden I'm getting all this foam. I'm wondering, what the heck is happening here? Well, I had opened a new bottle of the starting material, and I learned a lesson that I should have known: never assume or you get burned. Actually, never assume you become the first 3 letters. But anyways, I assumed the new bottle I opened from a reputable company that I'd used new bottles from was what it said on the label. And turned out it was an aldehyde. And after 6 weeks, when I'm going nuts with all, this is a lot of money on the line, my reputation, and I can't sell. Why can't I do it in the lab? I did it at least 40, 50 times. I said, what did I do differently? I realized this is a new bottle. What makes me think what they say is in the bottle is in there? And the answer was, it wasn't. There was a lot of impurity, and that impurity was that nasty, evil molecule, 2-ethylhexanoic acid. So that has a bad spot in my heart. Oh, let's do one more of these for fun. And why don't you try 2,2-dimethylpropanoic acid, draw the structure for that molecule. And I hope you enjoyed my sad tale of 2-ethylhexanoic acid, that evil, nasty molecule. Didn't know molecules could be evil and nasty. They can. I see one person's done. Give me a thumbs up when you're done, or I guess I shouldn't be discriminatory about the fingers in the hand, even though a thumb is not truly a finger. You can give me an index finger up too, so I'm not being prejudiced against the rest of your fingers in your hand. I think everybody's done. Let's do this. How do you do this? You start from the right, move left. OIC, and the word acid, carboxylic acid. And if that were an E, propane, 3 carbons. But it's not propane, it's a carboxylic acid. Now you can draw it on the right. Dr. White does on the left, but I like doing it on the right. So I have propanoic acid. So I keep on going, ooh, methyl, dimethyl, that means there are 2 of them. And where are they? Both of them are carbon 2. This is 1, this is 2. So I have a methyl there and a methyl there. I'll put in these hydrogens and I'm done. That's 2,2-dimethyl propanoic acid. And that's how you name carboxylic acids. Now, there are a couple of common names I would like you to learn, the structures of, and that is formic acid, acetic acid, and benzoic acid. It turns out, and I'll mention when I get to it, benzoic acid is also the IUPAC acid, a name for carboxylic acid. All right, let's look at formic acid. Now, carboxylic acids have this structure. Well, it turns out there's one where R can also be hydrogen, and this is formic acid. And this is a structure for formic acid that I'll draw it this way. You could also put the hydrogen. I'm going to do something I don't like doing. See, I don't even do it right because I don't like it so much. If you did that in a test, I'd look at it and say, yeah, that's right. And you could also do it this way, which I rarely do. I like showing the carbonyl carbon because I think that's cool. Now, formic acid, this is an interesting molecule. And why? How many of you have heard of the fire ants? Hopefully we'll never get them in Illinois. Those are those nasty little ants that have as a defensive weapon, they spray their attack with a mixture of chemicals. And if you get it sprayed on you, it feels like you're burning. And that's why they call it a fire ant. And what the fire ant is spraying is a mixture of hot water and formic acid. And what you're getting from the fire ant is what's called an acid burn, because I'll teach you either today or on Wednesday that this is an acid. It's called a carboxylic acid for a reason. Now, the next molecule is acetic acid. And I have some interesting news for you. Most of you have acetic acid in your house. No, I don't. Yes, you do. Let's take a look. Acetic acid is when R is a methyl group. And this is acetic acid. Nobody ever calls it ethanoic acid, diupac. It's always called acetic acid. How it got that name, I'm not sure, but that's what it's called, the common name. Now, Dr. White said it's in your house. It is. And let's take a look. If you have about 4% acetic acid, trying to do micro letters and it's not working. Let's do this. And about 96% water, we have a name for that compound or mixture, and we call that vinegar. Whatever vinegar you get, is essentially a mixture of acetic acid and water, and there might be some other minor things that give it the taste differential. Dr. White loves apple cider vinegar for different things I cook with. If you use rice wine vinegar, the best one is Marucan, the gold label, that I love. And vinegar is just a mixture of acetic acid and water. So if you ever have anybody over to do shots of vinegar, I doubt that, you can tell them, you're drinking acetic acid. Boy, you got to be desperate to do shots of vinegar. Don't. All right. Now, the last one is benzoic acid. And benzoic acid is both the IUPAC and the common name. And that's one R is in a carboxylic acid. Remember, carboxylic acid, R carbonyl hydroxyl group. This is benzoic acid. And that IUPAC, like you've seen before, in their infinite wisdom, decided, well, this has been called benzoic acid for eons. We're not going to change those organic chemists, so it's called benzoic acid as the IUPAC name. So remember, formic acid, R is H, it's the fire ants. Acetic acid, when R in the carboxylic acid is methyl, it's never called ethanoic, which is the correct IUPAC name. Everybody calls it acetic acid. And if you take some of that in water, you get vinegar. And if you ever go to the supermarket, you can see all different types of vinegar, and except for balsamic vinegar, where the water is a lot less and the acetic acid is more, and you get some things out of the oak barrel it was stored in. But for regular vinegars, essentially it's just water and acetic acid. Hold on one second. Dr. White's going to take you out into the real world. Not that I get any kickbacks from, but let's see if I come up with a big picture. This is the best rice vinegar, rice wine vinegar. It's also called Marucan. I can get it at my local supermarket, Valley, and I think they might even have it in Jewel. This stuff's not cheap, but it's worth and it's really great in cooking. It has a different taste than white vinegar, which has no taste other than vinegar, or apple cider vinegar, which I also like. Wine vinegar and champagne vinegar are nice, but I like this the best along with my apple cider vinegar. And one of the things I do with this is I make an oil vinaigrette dressing with this, and it's dangerously good. I mean, it's real good. All right.
Dr. White?
Yes.
Yeah. Real world example. About 15 years ago, I had some skin cancer on my neck, probably from sunburn because I didn't use my sunscreen. And they put it was acid from a beetle on the neck, which kind of it caused a boil. And would that be the same thing as formic acid or some?
I don't know. I honestly don't know. It could have been that. There are other acids they could have used, but maybe I would have to look it up on via Google to see what insects have what carboxylic acids. But I'm not sure which acid they use. If you've ever heard of, what do they call that? And somebody help me out, where you have a face mask, or they put it on acid skin treatment to help take off a layer of your skin. There's a name for that. when they put acid on your face. It's a cosmetic treatment. And there, I think they might use formic, but I'm not sure. They might use a dilute inorganic acid. So anyways,
Okay.
I'll tell you what, email me when you have a chance. I'll remember and I'll try and track it down.
Okay.
Thank you for your observation. All right. This slide for now, the switch is off. Will it be on a test? Later on, we'll talk about it. And you can have long chain organic the way I have written it. Where CH2 is repeated like a number of times. Lauric acid, its CHN is 10. Palmitic acid, CHN is 14. Stearic and oleic, which I'll teach you later on when we get into fats and oils, which I worked in. I actually came up with, at one company, 2 different types of oleic acid, high purity, that they're still selling now. I did that in 80, when was that? About 89, and they're still selling it 1990. That's, oh my God, over 30 years ago, and they're still selling my product. It's their product because I work for them. And these are all, and I'll teach you later, long chain acids. Long meaning the R group is very long. And a lot of these are in your hand lotions and cosmetics, and we'll talk about that later. All right, warning, warning. Dr. White's going to talk about some chemistry things you'll think about. Oh, is he talking about that? I'm just talking about the chemical part of it, not the moralistic part of it, okay? Warning. Switch is off, but I still like to talk about something. Here, my software drew it this way. You could also draw it this way. The common name for this molecule, which has 2 functional groups, both a carboxylic acid and an alcohol. Here's my alcohol, here's my carboxylic acid. Notice the hydrox group is on the alpha carbon, the carbon bonds to the carbonyl carbon. This is called lactic acid. How many of you have ever worked out real hard and you got that muscle burn? Have you ever seen what, I forgot, Running Man by Arnold Schwarzenegger, no pain, no gain. And Mother Nature has somehow put in our body a mechanism that when you've worked out too much, this will be in your muscles, and this gives you an acid burn, and it's called lactic acid. Now, here's the part, warning, warning. Dr. White loves to go into supermarket or big box stores. I don't know if it's a hobby, but it's a mental challenge of mine. And that is some new products. How the heck did I do that? And I'll go and look at the label, being an organic chemist. Those are molecules. That's what's doing that. Now, number of years ago, there's a company called KY, which makes personal lubricants for certain personal, how should I say, activities. And they came out with a new product called the warming gel, which during that personal activity, certain personal parts got warm. And Dr. White, me, thought, how did they do that? So I went and looked at I went to Walmart or Target, and they're selling it. And I picked up the bottle and looking at, oh my goodness, they had lactic acid in there. And you were giving your body a very mild acid burn. And that's how it got warm. Well, it turns out there's another way of finding things like that by patents, which I used to have a lab and students didn't like doing patents, so I took it out. But I can look up the patents. These are ways of protecting concepts for products companies make, and they changed it. They used to have lactic acid. I think some people got too much of a warming sensation from the acid burn. They took that out, replaced it with a long chain alcohol. And what happened was the heat of hydration the moisture on your skin forming hydrogen bonds to that alcohol was what caused the newer warming sensation. It was simple. Now, I sort of figured out, but I'm not sure if I did it totally, but I think I do. A couple of years later, that same company, KY, came out with a personal lubricant for that personal activity and personal parts of your body that was called fire and ice. I could see immediately the fire. It took me a while to figure out how they do the cooling safely to get the ice part. And that's a hobby of Dr. I don't know if you call it a hobby, intellectual pursuit, which is a benefit of this course, because you can go and look at labels and figure out how they do things. Now, another molecule I'd like you to, again, switches off, but I thought you'd be interested in is citric acid. And citric acid, and I'll rewrite it, my software didn't like the way I wanted it to, has 4 functional groups in it. And notice we have an alcohol, carbon with a hydroxyl group, 1, 2, 3 carboxylic acids. And citric acid, where can you find it? In lemons and limes. How many of you have ever bitten to a lemon or lime? And go, ooh, is that tart? You go, ooh, is that tart? Well, what makes it that? Ooh, that's tart or sour taste. It's the citric acid. And there's more citric acid in lemons than limes, which is why limes have less of that, ooh, tart taste to it than lemons. And I like limonade more than I do lemonade. And what I'll do is I'll go to the supermarket, my local one, buy some limes, cut them up, squeeze them in water, put some sugar in there, and enjoy it. I like that better than when you make lemonade, which is the same thing. Now, how many of you have seen over the last 8-10 years, there's been a trend in children's candy? The more sour it is, the more they like it. I don't understand why they do, but they do. You see those things with the big ring with a lollipop on it, and it's super, super sour. Well, what they do is they buy and put more citric acid. Now, years ago, organic chemists figured out a way how to make citric acid in a chemical plant and not have to squeeze lemons or limes. And those super sour candy, this has more citric acid into it. And that's what they do. Now, another important place is with citric acid, I'll teach you later, this molecule is used to make another chemical that helps keep the calcium level in our body if you take a supplement, or if you ever bought fortified with calcium milk or other things, they use citric acid. And later in this chapter, I'll teach you about that. But I thought I'd show you different acids in Mother Nature. And again, Mother Nature is the greatest of all, lactic acid and citric acid. It won't be on a test, but switch is still off. When we look at, I have acids, and because I worked in the acid, carboxylic acids, I'll sometimes not even realize I use slang. This should be carboxylic acid. Switches off here. Now, some of the shorter ones have sharp, unpleasant odors. If you've ever snorted a bottle of vinegar, you'll know what I'm talking about. And to ruin your day, oh, I will. In a lab someone managed to break a bottle of this on the floor, not me, but I was the manager, so I had to help him clean it up. I wound up throwing away. Luckily, I was at a company that had casual dress, the shirt and jeans. If you're an organic chemist, which I am, you always carry a change of clothes in your car in case you need to, and that day I did. This is butanoic acid. And the best way to describe what it smells like, I apologize, it smells like upchuck. If you threw up, this is what butanoic acid is. It's one of the most vile non-sulfur compounds I've ever smelled. Now, the lower molecular weight have sour taste. You saw that in citric acid, MW short for molecular weight. Vinegar has a sour taste. I'll talk later about their polar. They have higher boiling points because they can hydrogen bond, and the lower ones are water soluble. This will never be on a test or a final of mine, but I thought it covered some stuff. All right, switches back on. Now, carboxylic acids, why are they called acids? That's because they are acids. What's an acid? Quick review. From general chemistry, HA is any acid, and it'll dissociate to this where it gives up a proton. And any acid is a proton donor. And carboxylic acids are proton donor because they can donate a proton to water to form the hydronium ion. And let's see if I have it on the next slide. And since if we have an acid base, this is an acid, this is a base, can be many things, will form an anion, plus the base will accept the proton. That's the definition of. Therefore, carboxylic acid, this is the acidic proton on the oxygen. And notice I formed, it's called the carboxylate anion. I'll talk more about this later in this chapter. And this is the hydronium ion. What you get when you put an acid into water. And because a carboxylic acid can donate a proton, it's called a carboxylic acid, an acid. And that's really why formic acid burns like a carboxylic acid burn. Sad story. I have never gotten acid on myself. I've always been ultra careful. Years ago in an organic lab at the other school I teach at, I had a student who didn't follow directions in a lab. That was the nitration lab we did, and put a whole eyedropper of nitric acid, which is inorganic, on his forearm. Within seconds, he was yelling, and I was only about 2 feet away. I grabbed him, put his arm under cold water. It still was too late. And within a couple minutes, we sent him to the hospital for proper treatment. But the next time back in class, it looked like somebody had slapped metal on his arm and had that kind of scar and burn. And it was not pleasant for him. It was quite painful. That's why they call it an acid burn. And formic acid is a carboxylic acid, a strong acid. And that's why the fire ants have that weapon.
Excuse me, why are there two on the hydronium ion? Is that two positive charges or?
No, this is plus. Like
okay.
A plus B makes C plus D. This is just the end. Like this one right here or here. I'll always put the charge to the right superscript. It'll always be superscript above. It's hard to tell on this, but that's a good question. Thank you. All right, I'm going to turn the switch off for this slide, but still, what makes a carboxylic acid acidic? And let's look at the difference between ethanol and acetic acid. Now, if I take ethanol, and switch this off for the slide, but it's still good to know. I could draw this arrow like 10 times smaller, the top one. To lose a proton, this is not going to happen because this is a very, 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 very weak acid. The alkoxylate anion, this is a super strong base because it wants to go back here. Now, if we look at an example for acetic acid, here the equilibrium is a lot more to the right, meaning a stronger acid, or it's easier to move this proton off. Why? Because the more I can draw resonance forms, where I just move electrons, do this, because I can draw this, and these are different. I can label this different isotopes of oxygen. See, it's on both of these at the same time. This is two resonance forms, and that makes this structure more stable, meaning you're more likely to go to it, and that's why this is an acid, and that's acidic, as opposed to this hydrogen is not acidic. If you're reading a book, I'm skipping section 10.5. Aren't you glad I told you you didn't need the book? All right. Conversion of acids to their carboxylic acids switches on full. Remember, acid plus base gives us salt, proton transfer. Therefore, the first general reaction of a carboxylic acid, if you react a carboxylic acid with sodium hydroxide, you'll get this carboxylic acid plus water. Since I asked for give the organic product or products, you don't have to put down the water. Now, watch closely, because since I've written these slides, I've modified this. Now, the water you don't need. Now here, M for our class will be lithium, sodium, or potassium. That's something I thought I'd extend, because later on in the semester, I'll talk about how when doing this with lithium hydroxide to making these type of carboxylate anions, where M plus is lithium plus, has found a place in our daily use, like for a lubricant in my garage door. So let's take a look at this reaction. Carboxylic acid plus a base, either lithium hydroxide, sodium hydroxide, potassium hydroxide, gives me a carboxylate anion. And the question would be, and I haven't done this in a while, so I better ask. Thumbs up, people. Can you see that? Thank you. If I react this compound with this, what's the organic product or products? Well, what's different here? Ooh, carbonyl hydroxy group carbons, carboxylic acid. Hydroxide base with a cation or a alkali metal cation. Number M can be sodium, lithium, or In this case, it is potassium. And I have an acid-base reaction. This is an acid, this is a base, and I'll get my carboxylate anion. And you get water, but you don't have to put that down. And therefore, what's our this? You don't break carbon-carbon single bonds. It's still attached to carbonyl like it's here. But now this will be a carboxylate anion. And what's M? Potassium cation. And I know there are 4 bonds to carbon, so I'll put in my hydrogens. Now, there's something important I want to talk about. Notice here, I put O minus K plus. I always do that. Good habits, Dr. White doesn't break, and I think that's a good habit of mine. Now, a couple of years ago, I had a student in 170 who said, why do I have it? I took off a point or so on a point on a test because he didn't show the charges. He got upset. I said, cool down. You prove to me why you don't need to show charges, and I'll give you the point. It was only 1 point out of 100, but he still wanted every point, and there's nothing wrong with that. So he did the following. I still remember, as he says, for this compound, sodium chloride, remember, please pass the NaCl, do you write it this way or do you write it this way, which it actually is? I say, I write it this way. And he said, then why can't I write this like this? And I said, no, you're right. So I gave him his point, and ever since, you can do it either way, just like here. You could have this okay, I guess it's okay. Oh, that's awful. But anyways, I will never take points over. I like to show the charges because I think it looks right. But if you don't, if you write it this way, it's okay.
Wouldn't there be another carbon in that one?
Hold on. Guys, let me turn up my volume on my speakers. Could you please repeat the question?
In the answer for the last one, wouldn't there be another carbon?
Hold on. You're right. I made a mistake. Thank you very much. It's that snowstorm. Well, I got to blame it on something. Oh, Dr. White made a mistake. I'm human. Thank you very much. Better keep an eye on me. I made 2 mistakes today. All right, let's try one. And why don't you give the product or products for the following reaction? And it would be organic product or products. And again, thank you for finding my mistake. I appreciate not the mistake, but you helping correct it. Thank you. All right, see, thumbs up people are already on it. So when you're done, give me a thumbs up. And good news, you don't have to drive in the snow to go home from my class. Anybody need more time? All right, let's do it. What do I have here that's different? Carbonyl with a hydroxy group, carbons, carboxylic acid. What am I reacting to? This is NaOH, sodium hydroxide, MOH. Hydroxide is a base, and M can be sodium, lithium, or potassium. Can be other things, but I'd write different bases. I'm going to stick to this for this class. And it's a straight acid base, and you get the carboxylate anion. What's our this? So I better count 1, 2, 3 methyl, my carboxylic acid, which is now a carboxylate anion. What's M? Sodium. One, two, three, 4 across, 1, 2, 3, 4 across, methyl, methyl, done the right thing, and I'm done. And with that, I looked at the clock, and guess what? Sad thing, we're out of time. And don't forget, tonight, I have my office hours from 50 minutes, an hour and 15 minutes, from 6 to 7:15. If you need help, stop by. That's why I'm there. And with that, I'm going to end with my world famous ending. Gang gesund. Goodbye. I'll see you on Wednesday.